In this video, we are going to look at simple harmonic motion, specifically with respect to time. So remember, there are two ways to frame our simple harmonic motion. One is respect to positions, with respect to x. So make sure you're okay with that, or you'll watch this after the video. Okay, this one, the relationship is to be studied with respect to time, t. Okay, so all the equations that we'll be writing in this video will be in terms of t. And we're going to run through kinematics and energy also. So start first. Look at this cute little spring. It's going to oscillate up and down in a very predictable fashion. And in fact, because it's so predictable, let me show you something really cool. Look at this. Okay, so if you observe the spring, right? This spring that is oscillating up and down, this purple spring. If I shine a light, okay, from the left side of the screen, I shine the light off, you will see that this green color thing is like a shadow projection. Notice that? It's a shadow projection. So wherever I pause, depending on where I pause, doesn't matter, wherever I pause, this is where the shadow of the circle will be, shadow projection. So if I look at the perspective of the circle, it is actually traveling in simple harmonic motion. Okay? And then at the same time, that circle will go upwards if the spring is moving upwards and will move downwards when the spring is moving downwards. So to describe this oscillating simple harmonic motion, you will notice that it is mapped together with a sine curve. Pretty cool, right? So if let's say I pause this one, at any given time, all three will have the same, they're on the same line. So this means sine graph can be represented by a circle. Motion of a spring can be represented by a circle. Everything is a circle, it's a conspiracy. No lah. Okay, so if you learn a bit of maths, this is where we talk about polar coordinates. This is where we talk about why we study so intensively about the Trigo function. If not, it's just a cool coincidence, all right? Let me show you something different. Okay, see behind me, you have a particle in simple harmonic motion. It's just going left, it's going right, it's having its own good time. But let's think about the 3D view. So if you look at the particle moving in circular motion, and hopefully you've already learned circular motion, it's the previous chapter. If you look at it from the plane that it is moving in the circle, it means that it's actually in simple harmonic motion. See? It's oscillating left, it's oscillating right, but in the 3D plane, it could be moving in a circle, or it could be oscillating left and right. Okay, so this is the circle view. And sometimes if you look from the top, you definitely get the see the object that is traveling in a circle. But teacher, why got wave view one? Let me show you. Is it familiar? This is a transverse wave. Okay, you will see that the wave pattern looks like it's traveling from downward to upward. Maybe I remove the circle. Do I show the circle? I'll show the wave. Okay, so this is a transverse wave. So from this perspective, if I don't give you any context, you will say, okay, this is transverse wave. The wave profile is moving vertically. The wave profile is moving like that, up and down, up and down. But the particle is moving left to right. This is transverse, correct? So this is why all wave particles are actually in simple harmonic motion. That's why we study simple harmonic motion. That's why we talk about energy from the perspective of simple harmonic motion. So from here, you can see that this is the wave view, right? And if I show the circle, and then if I guess, show you the 3D view, this is actually the motion of the particles. So it's pretty cool. There is an intrinsic relationship between a particle in circular motion, a particle in simple harmonic motion, and waves. We just need to tweak the description or the variables. So cool stuff, all right? But just to make our life a bit easier, we are going to stick to this. Okay, don't have that one yet. Wait lah, you wait, you go uni first, okay? I'm going to stick to this one. So let's back up and look at this. We are now going to try to come up with a general equation that describes this motion of the spring. Spring is going to oscillate upward and downwards. I'm going to call, I guess, again, I like to call it A, but you may call it X naught, right? So this is the amplitude. I'll call this A. And the amplitude down here will be negative A. Okay? Period here is T. So one complete cycle is T. Why does this look like your wave profile? Because they are the same thing. This is one wave particle. I mean, not same. They're similar, related. This is one wave particle. Okay? So we're looking at a single wave particle. So from here, to find the equation of displacement, just to frame it for you, I want to find an equation of displacement x in terms of time t. So I want x in terms of t. Okay, so the equation that we will use, if this one looks like a sine graph, right? So x will be equal to a, where a is the maximum, sine, and we need a constant inside here to represent how many cycles per unit time. Okay, and that constant will be our good old omega t. Okay, let me highlight the variables. The variable here is time and the displacement or the position of the particle. Okay, so of course you can't have displacement with displacement. So displacement with time makes a lot of sense. Okay, so here is how you can link. If let's say, for example, I want you to find where is the particle at 2 seconds after the oscillation has started, then you're going to put 2 seconds into this equation to help you find your x. This is a general one. So those of you who are a little bit more perceptive may be thinking, teacher, well, sure, we could start with here. So this graph starts from 0 because the timing starts from here. But the timing can start from here or can be cos. Can also start from here, negative sine. Can also start from here, negative cos. So here is where I'm going to tell you if you are confusion about sine, cos, negative sine, negative cos, and you don't know how to differentiate them, go and watch, or you forgot that because it's been a while. Okay, go and watch the maths booster video recorded by Miss Ellie. Should be somewhere in the channels. Okay, go watch how to differentiate, because this is what we're going to do next. Once we have displacement, of course, we're not going to stop here. We're going to have to find the velocity of the particle. But how do we do that? We are now going to differentiate. So if you don't know how to differentiate functions like this, or you don't know what I mean by sine can become cos, cos can become negative sine, go watch the maths booster video, then come back here. Okay, I'll be waiting. Okay, so we're going to differentiate displacement with respect to time to find something in terms of v. So this is v, this is t. Okay, we're trying to be able to find v in terms of t. I guess I want to start with x. So x is equal to a sine omega t, and v here would be equal to dx over dt. I differentiate law. Okay, so when I differentiate, I will get sine becomes cos omega t, and then I throw out the constant. Here will be a omega. Okay, so whatever that is in front here, this a omega is your v naught or your v max. So normally they call this v naught or v max. Okay, so this value here, your v naught, is a omega, and this one will be negative a omega. And how do we draw a cosine graph? Okay, now look at this sine graph. We're going to shift it 90 degrees to the left. Okay, or I could do this. So I'm going to draw a cosine curve. Okay, but I'm going to trace this one so it's easy for me to translate it a bit. Hello? Okay. So cosine curve will look like this. Translated lah. Okay, more or less. This is your cosine curve. So the phase relationship will be shifted 90 degrees. Okay, if you don't want to think so much about that whole phase relationship thing, then you could consider from the perspective of cosine. Okay, so this is cosine. You can think about the gradient. So like for example, at this position here, let's say this is position yellow, the spring is at the highest point. So at the highest point, what happens to the velocity? The velocity is actually 0. Because, it's stopped. And then it will accelerate downwards. That's why you see the velocity is negative and getting bigger and bigger, bigger and bigger, bigger and bigger. Then this point, this purple position here that I'm highlighting, this purple position is where the speed is the greatest. And then if we trace back up this line, correct, is the greatest at equilibrium position. So it makes sense, It makes sense every single point of the way. This is the beauty of calculus. Do you need to know the equation? Well, remember I showed you before, or maybe I have not, depending on what videos you're watching. The velocity of the particle is given, this list is given in your second page, third page, front pages of your exam paper 4. Okay, so this is the first one. Okay, so that's it. Just a reminder that we don't always start with sine. We can start with other terms, go and do some past year questions. Okay, but sine is the general one. We need to start somewhere. Okay, so since we have velocity, we can now travel down and do acceleration. Acceleration means I differentiate velocity again, dv dt. Okay, so if I differentiate velocity again, what I will have now, my A will be, you differentiate cos, you get negative sine. Okay, so assuming you watch the maths booster video or you're familiar with this, you get negative sine. Okay, negative sine, but in front here, you will have to multiply by another omega. So this is A omega square. So from here, you will find a few information. First one being the maximum acceleration. You can call this A naught. You can call this A max. Okay, it will be omega A omega square. Can be plus minus. So it will be A omega square negative A omega square. All right. Second thing, teacher, you see wait this A and this sine omega t, isn't this the origin? The original equation, correct? Because sine and cosine is actually cyclic functions. You differentiate a few times, you get back the same thing. It's not a conspiracy, okay? It just happens to be that way. All right, so this one is actually this one. Is this the same? Okay, so then I can substitute, right? I'll write here for you. I'll say something along the lines where since x is equal to a sine omega t. It's a sine omega t. So then I have a is equal to negative omega square x. Wow, teacher, we are back at the defining equation of simple harmonic motion. It's like we went one big round and then we are back here. Yeah lah, that's why this is the defining equation of simple harmonic motion. No matter where you run, no matter where you go, a is proportional to negative x because you're oscillating. Okay, let's draw a negative sine graph. So remember, we started with sine. Sine was like this. Okay, then when we get cos, we move 90 degree. Bloop. So whenever you differentiate, you move 90 degree. Differentiate again, move another 90 degree. Bloop. So 90 degree is quarter cycle. Okay, I show you again. We started from here. This is sine. Differentiate sine, you get cos, move 90 degree. Differentiate cos, you get negative sine, move another 90 degree. Like that, negative sine. Oh, if you don't need it, you already know how a negative sine graph look like. Great. That is OP as well. Okay, so let me delete the excess first. Okay, so you will get a graph like this, where this graph is actually negative, this graph, shape-wise. Okay, so a few things that is important for us to stop right now. Let me label the axis first. This is acceleration against time. Number one, you will notice that we always concern ourselves with maximum value. Okay, so generally I'll tell students, you want to find maximum value? Can. Let's talk about max values. I write here. The max values for displacement is equal to x0 or a. Makes sense, right? Amplitude. Max value for velocity will be omega x0 or omega a, or a omega. So basically we multiply by omega. But teacher, why we multiply by omega again? Because we differentiate. When we differentiate the function inside here, this omega t that we differentiate, we throw out the omega. So we multiply by omega. And then for acceleration, we multiply by omega 2 times because we differentiate 2 times. So then this maximum acceleration, A max, will be equal to omega square x0 or omega square a, or a omega square, depends on you lah. So this one is all maximum. Okay, cool. So this one, if you know, then all the questions are quite easy. If you have amplitude, if you have angular frequency, which is omega, your life is easy. So if you want to brain a system, you look at the system, you don't know how does it work, try to find out what the amplitude is, try to find out what the omega is, and sometimes they will actually ask you to find that in the question. Okay, so a few really nice things about these graphs is that if you understand both graphs from the left and right behind my head, okay, you will notice that they have the same maximum value. You see, this maximum value of velocity is a omega because we differentiate. But the maximum velocity also happens to be a omega here when we use this equation. So both equations actually agree with each other. What? No fighting, okay? No fighting. Both equations agree with each other, okay? Next, if you look at acceleration, we start with the definition equation. We also get maximum a omega. You differentiate a omega square. You differentiate 2 times. Your maximum also a omega square. It is perfect. Perfection. Okay, so that's why both graphs are drawn side by side, and that's why the maximum value have to agree with each other, because we are analyzing from 2 different perspectives. So all the technique on this side is with respect to time. Okay, if you want to know, or if you haven't yet, then go and watch the video with respect to position. But now we're going to move on to look at simple harmonic motion with respect to energy. But as usual, when I want to think about energy, it's useful to think about kinetic energy first. So I am going to bring in the velocity against time graph again. Okay, so you can see I brought the VT graph over here. Okay, and I'm going to try to draw energy against time. Okay, let's think about the easiest one, kinetic energy. Energy against time. You want to put unit, can? I put joule lah. Alright, so kinetic energy, KE, is equal to half mv squared. Okay, so let's say I look at the velocity, right? The velocity is maximum. I mean, the speed is maximum at all the purple points here. So here is where the value of v is maximum. Meaning at all these points, here, 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 and here, the velocity and the kinetic energy is maximum. So here is KE max, because here is V max. So all the purple dots that I stashed. Okay, teacher. So we're going to have maximum value here. Got 0 points. Got here, here, when the velocity is 0. So all these points here that I'm marking out, these points are when velocity is 0. So let me try to label it to the side. Here, velocity is 0. So here, KE is 0. Ooh. Can we now put them together? Sure. You tell me what shape you want to draw. Sinusoidal, right? Because the pattern already looks very sinusoidal. So I'm going to draw out a sinusoidal function. Okay. This is actually a sine square graph, or a cos square graph. Sorry. It's a cos square graph. So the reason why this is a cos square graph is because you square velocity, right? So you're going to get a graph that's shaped something like this. Okay lah, good enough. I am satisfied. Okay, but you may be thinking, teacher, got equation or not? Got. I can give you the equation. No problem. So the equation will look something like this. I'm going to start with KE is half mv squared. But if you remember this equation, V is equal to A omega cos omega t. We derived this already. You go back and see, just drag the progress bar. Okay. So from here, you will have KE is equal to half m A omega cos omega t squared. Now, before you panic, don't worry. This is half m A square omega square cos square omega t. So beautiful. This is a cos square graph. And then you may be thinking, teacher, the cos square graph and the cos graph, the shape the same. Well, let me show you. Okay, here are how the shapes are different. Okay, so the green graph, this one is cos x. The blue graph is cos square x. Okay, you see, when you square 1, you get 1. When you square -1, you get 1. Okay, but if you square values that is less than 1, you get smaller value. That's why the cos square graph is below the green color cos graph. But in this case, if I sketch the blue graph without the green graph there, you can't really tell. You can't really tell that it doesn't matter. And if it doesn't matter, then this shape is OP is fine. Okay, but this is actually a cos square graph. Teacher, GPE there. So let's look at the potential energy of your simple harmonic motion. So you may or may not have seen this before, but here is to illustrate or to show you the conservation of energy for a system in oscillation or simple harmonic motion. So I want to slow the system down, and you can see that no matter how the green color kinetic energy changes, the potential energy will change reverse to what is happening to the kinetic energy. So one will increase and the other one will decrease. When green decreases, KE decreases, PE increases. But the total of this graph at any point is equal because no energy is lost in the system. Okay? So that means they have kind of like if one go up, the other one will come down relationship. Okay? So if that's the case, then the graph that we expect to draw for this would be, for example, when the kinetic energy is increasing, I kind of expect the potential energy to decrease. And if the kinetic energy is decreasing, if I can see here, then this one should increase. So I kind of expect to get a graph that looks like this. Kind of like a zigzaggy. So some of you who are a little bit perceptive may be asking yourself, teacher, is this sine square? Well, let's see. Hang on, this is KE. Why did I draw the arrow this way? Kinetic energy. Okay, so I have an equation for kinetic energy, and then you may be asking yourself, can I find an equation for potential energy? Can, but before we go there and think about the conservation of energy, this part here is the maximum KE. It's the maximum KE because the maximum value of your cos square omega t is 1. So whatever you have in front here, you can put here. Half ma square omega square. And coincidentally, half ma square omega square can also be written as half m a omega square. So this one is V max. Pretty cool. Okay. So if this is the maximum kinetic energy, and I know that the total energy is KE plus PE, so let me write that down for you. Total energy is equal to kinetic energy plus potential energy. However, total energy is also equal to maximum energy. When you add these two graphs together, you will get something like a constant horizontal line like this. This is your total energy. Okay, so I'm going to write here. This one is total. So if I substitute into this equation pretty quickly now, this will be half ma square omega square is equal to half ma square omega square cos square omega t plus PE. So from here, I can rearrange, PE will be equal to half MA square omega square. You see these two is the same thing. So I can factorize, right? So when I factorize, I will get 1 minus cos square omega t. I take these two out, I factorize. So when I factorize it out, I get half MA square omega square 1 square omega t. What is 1 square omega t? If you're good in Trigo, or if you're familiar with Trigo, this will be half MA square omega square sine square omega t. So one is cos, one is sine. Do you need to know the equation? Not really, no. I just show for fun because I like Trigo. Okay, you don't need to know the equation. What you need to know is how to interpret the graph. You know how to see where the maximum, where the minimum values is. You know how to, very importantly, tell the period. Here is a nice trap to trap students who don't know. This part, it looks like one complete cycle, but actually this is t over 2. Because you think about the velocity, we've only traveled half cycle. It is the square that introduces an extra period. There. When you square something, you introduce the extra period. So just a side note lah. You don't need to know the equation. What you need to know is this one. Total energy is KE plus PE and the maximum value. KE max is equal to PE max, which is equal to half M A square omega square. These are the important things. The equation, I just show for fun. Okay, so if you have watched the displacement video, okay, if not, then you can watch after this. You can also once again see that the maximum value is the same, my friends. So the maximum value will agree whether it's displacement against, whether it is in terms of displacement or whether it's in terms of time. The maximum value is still half M A square omega square based on our analysis lah. And if you want to find an expression or an equation for potential energy for this one, your work or your extra work could be do this process again and minus. Okay, so that could be in that video. So if you haven't watched this one yet, go ahead. So in this particular recording or this particular video, we have looked at the time-dependent relationship. So with respect to time, we'll have all these equations. What is important is not really to memorize, but to understand the process of differentiating. But if you are not good in maths, or you're not doing maths, or you don't differentiate, or sure, shift the graph. Okay, shift the graph, learn to shift it, because that will help you tell. And then from here, you can also decide that, it kind of maps correctly or perfectly. Okay, so properties of the graph. I'm going to now show you a final simulation. Okay, so you probably may or may not have seen this before, but you can see, or you can tell that the mapping for this is the displacement, velocity, and acceleration graphs that we are familiar with. Okay, so every time it's differentiating and differentiating. And you can see the maximum value for both are the same. Velocity is A omega, acceleration is A omega square, and kinetic energy is half M A square omega square. Very important to know how to read omega and amplitude from all of this graph. Okay, so important skill is you know how to get amplitude and omega period or frequency from this graph. Okay, or they give you period, frequency, amplitude in the question and you sketch out the graph. So it's an either or thing. That is an important skill that you should have for your oscillation. Interpret the graph, get the constants A and omega. Or given the constants A and omega, sketch the graph. That's it for the theory part of simple harmonic motion, time dependent. And hopefully, if you haven't watched yet, then go watch the position dependent one. Both left and right are important. And both left and right can be connected by this equation, displacement and time. You can't plot displacement against displacement. That makes no sense. Alright, that's it. I'll see you in another video. Have fun studying.